Hi everybody. In this video we're going to start looking at general chemistry, which is what we're going to cover basically for the first test in thanatochemistry. If we look at the definition of chemistry, or what chemistry generally is the branch of natural science that is concerned with description and classification of matter. So looking at describing the characteristics of different types of matter, then classifying it, putting it in categories, and then changes in matter. So what happens when they go through either a physical or chemical change. We also, in chemistry, look at energy associated with those changes. Now, in this class, we're not going to look too much at that. That involves equations, which we're not going to do, but chemistry is interested in that, certainly. You can divide chemistry up into a few different categories. The three main categories would be inorganic, organic, and biochemistry. So inorganic chemistry is the study of elements, excluding carbon-containing compounds. So things like salts, bases, acids, things along those lines. As long as it's not a carbon-based compound, it's inorganic chemistry. So when you take general chemistry, that tends to be inorganic chemistry. Organic chemistry is the study of carbon-containing compounds. So compounds that have carbon as a backbone, if you will. So that would be your alkanes, alkenes, alkynes, arenes, alcohols, ketones, esters, ethers, aldehydes, which is an important one to us. Things along those lines. Those are all carbon-containing compounds. Carbon-containing compounds that are created by biological entities is the purview of biochemistry. So biochemistry is the study of compounds produced by living organisms, and most of those compounds are organic in nature. Now, two divisions of chemistry that concern us would be embalming chemistry, which is the study of changes in matter that are related to disinfection and preservation, so how our chemicals interact with the compounds of the body for disinfection and preservation. And then thanatochemistry, which is looking at the study of antemortem and postmortem chemical changes. Antemortem is before death, and postmortem is after death. So thanatochemistry is looking at how the body's chemistry is changing before and after death that may affect our embalming process. So some of the properties of matter, you have either physical or chemical properties. Physical properties are characteristics that are observed without any change in chemical composition. So as long as the matter that you're looking at does not change chemically, that is a physical change or physical property. An example would be state of matter. So gas, liquid, solid. Ice is just frozen or solid water. Water is liquid water. Water vapor is gas water. It's always water. The chemistry has never changed. It just changes its appearance, if you will. Solubility is another physical property of matter. The ability of two substances to mix. And we'll talk about solutions here in a bit. Density is also a physical property. So density is the ratio of mass to volume. So you have, depending on what you're looking at, so for instance, I'm about 5'9", I weigh about 200 pounds. My density is a lot different than somebody who is 6'5" and 200 pounds, and a lot different than somebody who's 4 foot and 200 pounds, because you're sticking the same amount of mass into different volumes. And so density is kind of a measurement of that. Specific gravity is kind of an interesting one, and it's not one that we use a lot. The definition is a ratio of densities using density of water at 4 degrees Celsius as a standard. And so you're comparing the density of something to water at 4 degrees Celsius, so basically just above freezing. About the only time you'll ever see specific gravity is usually in a lab environment, but also it can be used as a way of describing concentrations. So if I say there's 50% of formaldehyde in a solution, that is, you could say its specific gravity is higher than something that is 10% formaldehyde in solution. It's a gradation of density. Some chemical properties of matter, which are properties that you see only in relationship to a chemical reaction. So characteristics that are observed resulting in changes in chemical composition. If you're looking at chemical properties of matter, that matter has to go through and change into something completely different. So some chemical properties would be things like combustibility, its ability to go through combustion. Combustion is defined as rapid oxidation, or the reaction of fuel and oxidizing agent producing heat. So, for instance, if you burn a log, the log is the fuel, the oxidizing agent is air, oxygen, and that produces heat. So wood has pretty good combustibility. Another chemical property would be reactivity, the ability to go through a chemical reaction, and maybe even better said, how easily does it go through a chemical reaction. So if you have very high reactivity, that means you don't need a lot of energy to make something go through a chemical reaction. Whereas you have a very low reactivity, it means you're very stable. And a lot of the chemicals that we use in embalming are very stable. They're very low reactivity, and that's something that you want. You don't want things that react very easily. That leads to things like explosions. When we look at changes in matter, there are physical and chemical changes. Some of the physical changes would be things like solvation, otherwise known as dissolving. Solvation is the clustering of solvent molecules around solute particles. The example I always give is Tang. I take a spoonful of Tang, I put it in a glass of water, and I stir it up. In this instance, the water is the solvent. That is the thing doing the dissolving. It's not what is being dissolved, it is what is doing the dissolving. Another way of describing a solvent would be the component of a solution that is in the greater amount. Okay, so it's the thing that is in the majority of the solution. In my example of Tang, I take a spoonful of Tang, I put it in water. The water is the solvent. The Tang is the solute. It is the substance that is being dissolved in the solvent. And again, you could use the definition of the component of the solution that is in the lesser amount. And we'll talk a lot about solutions and solvation in a later section. Another type of physical change are changes in state or phase changes. So from liquid to solid, from liquid to gas, from gas to liquid, so on and so forth. So these are dependent upon heat or energy. Putting heat into a system will do one thing, taking heat out of a system will do another thing. That change in heat is described as enthalpy. That's the heat gained or lost by a system at constant pressure. Now, why they say constant pressure is because if you variate the pressure, then you need less or more heat depending on what you're trying to do. So that's what they always say, constant pressure. When you add enthalpy to a system, that I always think of molecules as vibrating, atoms as vibrating. And so when the enthalpy goes down or you take heat out of the system, then the molecules don't vibrate as quickly, and so they start to solidify, i.e. freezing. If you add heat to the system or increase enthalpy, then the molecules vibrate more, and so you get more chaos in the system. So it goes to liquid or even more chaos, which would be gas. So changes in enthalpy will create changes, or I should say, before I move on to that, Systems always attempt to reach the lowest possible energy. That is true. That's why if you blow up a balloon and the gas molecules are vibrating very rapidly at that point in time, eventually that balloon starts to deflate. And it's not because it's lost gas, it's that the energy in those molecules has gone to the lowest state they possibly can, and so they don't expand as much. Now again, when you change enthalpy in the system, you will change the entropy in the system. Entropy is the amount of disorder in a system. Solids have very little disorder. They're very orderly because they have had a lot of enthalpy taken out of their system. But if you take, ice, for instance, ice is very orderly, very systematic. You've taken a lot of the heat out of it, so it's frozen. But if I start adding heat to the system, then the solid water turns to liquid water. Much more entropy, disorder in the system. Your puddles spread. They don't hold a necessary form. If I heat it up even more and boil it, then it turns into water vapor, which is a gas. Lots of entropy in that system. So as enthalpy increases, as you add more heat to a system, you increase the entropy. As you take heat out of a system, then you lower the entropy. So again, as an example, if adding heat to ice, which will increase the enthalpy because I'm adding heat to that system, turns that solid ice into liquid water, which would increase the entropy. So entropy and enthalpy are directly related. If one goes up, the other goes up. If one goes down, the other goes down. Now these changes in enthalpy do have some guideposts, if you will. One of those is the heat of fusion. The fusion means to melt. So the heat of fusion is the heat or amount of energy needed to convert 1 gram of solid to 1 gram of liquid. This is not a temperature. This is an amount of energy, usually measured in joules. So it would take much more energy to melt gold, let's say, than it would to melt water, to melt ice. Now, each type of matter does have its own temperature at which it will start to melt, and that's the melting point. So whereas heat of fusion is an amount of energy, the melting point is the temperature at which a solid becomes a liquid. Now you'll also notice that the melting point, the temperature at which a solid becomes a liquid, is also that matter's freezing point. So water, for instance, will freeze at 0 degrees Celsius, but it also melts from ice starting at around 0 degrees Celsius. Now, to go from a liquid to a gas, that is the heat of vaporization. So again, this is the amount of energy or heat needed to convert 1 gram of liquid to 1 gram of gas. The temperature at which that will happen is called the boiling point. So the temperature at which a liquid becomes a gas, temperature, not amount of heat, is the boiling point. And certain liquids take a lot of energy, so have a high heat of vaporization, but will not necessarily have a high boiling point. Water is a good example. Water will boil at 100 degrees Celsius, but you need a lot of heat, a lot of energy to make it turn into water vapor. And that's why I tend to say if you're going to get burned by boiling water or steam, take the boiling water. The steam burns a lot worse than boiling water does. Now we've been talking about these changes in state. There are two different types, two main categories, if you will, of state changes. One is endothermic and one is exothermic. The endothermic changes require heat. You have to add heat to the system to make them go. So for instance, melting, also called fusion or liquefaction, that's turning a solid into a liquid. When I have a liquid and I want to turn it into a gas, that is called vaporization. Now, there is a type of endothermic change that goes directly from a solid to a gas, and that is called sublimation. Dry ice is a good example of this. Dry ice is solid, but if you let it start to quote-unquote melt, it doesn't melt, it sublimates. It goes directly from a solid to a gas. which is why they use it in shipping a lot of the times for cold things. Then you don't end up with a puddle of water. We use dry ice in funeral service to ship bodies, and because it doesn't make a mess. The other type of state change is exothermic changes. Exothermic changes release heat. They lose heat from their system. So this is kind of going in reverse. So freezing is liquid to a solid. The liquid is losing energy, and so it turns into a solid. Or condensation, which is also called liquefaction because it's turning into a liquid. That's a gas to a liquid. Again, the gas is losing energy, turns into a liquid. Or to go directly from a gas to a solid, that is called deposition. And deposition usually happens in solutions, by and large. So those are the physical changes that you can see in matter. So some of the chemical changes that you can see in matter, especially ones that pertain to us specifically, would be things like decomposition. Decomposition is breaking down compounds into simpler compounds or elements. Your body is made up of polymers, which are kind of like repeating units of smaller molecules. And so decomposition breaks down those bigger molecules into smaller molecules that microbes can eat, and they will break them down even further. We also have cremation, which the definition of cremation is reduction of a body to inorganic bone fragments by intense heat in a retort or chamber. But basically cremation is just really sped up decomposition. At the end of both processes, you end up with CO2, water, and inorganic bone. Embalming is also a chemical change. So when we introduce embalming solutions into the body to disinfect, temporarily preserve, and restore the dead body, we are changing the biochemistry of the body by doing that. So those are all chemical changes. Now we've been talking about these different changes, both physical and chemical, and a lot of times they require energy. So the definition, at least in chemistry, for energy is the ability to do work. Oftentimes, energy in chemistry is synonymous with heat. Now, there are different types of energy. There's potential energy, which is an easy way to think of potential energy is stored energy. So this is energy possessed by virtue of position relative to other objects. If I put a car at the top of a hill and it doesn't move quite yet, that's potential energy. It's not moving, it's at the top of a hill though. If I were to push that car just a little, not pushing it to give it a lot of acceleration, just enough to break it over the precipice of that hill, what's going to happen? The car's just going to roll all by itself. That stored energy, because of the virtue of that car being at the top of the hill, is now going to turn into moving energy, which is kinetic energy. And so kinetic energy and potential energy are kind of based on gravity a lot of the time. At least that's when they first started thinking about energy. Those are the two main categories that came up. We also have chemical energy. Chemical energy is stored energy in chemicals that gets released during reactions. A good example of this is gasoline. Okay, gasoline just sitting there does nothing. But if you spark it, then it explodes essentially when it's in a cylinder. And so chemical energy doesn't do anything until it goes through some kind of chemical reaction and then releases that energy. As I mentioned before, energy in chemistry is oftentimes synonymous with heat. And so in heat in chemistry is energy transferred from one object to another due to a difference in temperature. If you put your hand on a cold countertop, okay, why is it cold? Because there's a difference in temperature between your hand and the counter. Eventually, that counter will start to feel warmer, and eventually you won't even really feel a difference in temperature because you've transferred heat from your hand into that countertop. Now, the thing with energy is that energy can't be destroyed, created, it just gets moved around, it gets changed. And that is the law of conservation of energy. The law of conservation of energy says that energy cannot be created nor destroyed. It can only be conserved. It can only be changed into some other type of energy. And so energy that is lost by a system equals the energy gained by its surroundings. Okay? If I go out with no clothes on in the middle of the winter, I'm going to lose a lot of energy from my body, but the surroundings are going to absorb that energy. So it's not like it disappeared, it just got gained by something else. And as I mentioned, energy can only be transformed into another type of energy. It can't be destroyed, it can't be created, it can only be changed into something else. So that finishes it up for this section. In the next section, we're going to look at different states of matter.